still in this presentation, you will learn a bit more about a bit different perspective of driver activity recognition and driver activity prediction inside the car. So we're doing this kind of transition to the topic of intelligent vehicles, intelligent driving. So let me see if it works with slide transition. Perfect. So first, let us motivate our models a bit. Why do we even need to look at the driver? And the main motivation is, well, driver engagement in some secondary tasks in fact increases accident odds. We see there several several Tesla accidents caused by people watching Harry Potter, playing video games, and so on. And in fact, this is also empirically shown. There are studies which show that between 10 and 30% of accidents are caused by secondary activities. And also some worrying evidence that in fact 30% of time drivers are engaged in secondary activities. Of course, it is a question what you define as a secondary activity. Now I have to mention that of course with progressing automations, the cars get more and more intelligent. It also kind of becomes safer to be distracted because intelligent vehicle kind of takes over more and more of the driving part. So the safety, so getting engaged into destructive activities is becoming safer, but at the same time, people are doing this more and more frequent. And this is why one motivation of our work is in fact to identify secondary activities, to identify driver distraction. But of course, it depends on the level of automation. So at the moment, we did not reach full autonomy yet. So yes, in fact, right now we want to identify what the driver is doing to kind of predict how long will he or she need to take over the control of like semi-autonomous car, or also to predict maybe that the driver want to do some dangerous maneuver so that we can interfere earlier. However, as we progress within degrees of automation, let's say, let us assume the car is fully autonomous, then we can also observe the driver for comfort. So for example, if we detect that the driver is drinking coffee, we can adjust the driving dynamics accordingly, or the driver can communicate via gestures. So today we're going to talk about vision-based driver observation. And as you know, computer vision, we want to recognize what is happening in images. And today it's almost always addressed with deep learning. For a long time, CNNs, now it's visual transformers, and we get very, very good results, impressive accuracies on many data sets. But is the problem solved? And as you know, there are still a few problems. So first, we have the high data collection and annotation cost. And for many tasks, you can already use very large pre-trained foundation models, and it will give you very nice results on new data sets, but it's still quite hard for very specialized applications. For example, inside the vehicle, you don't have many similar examples present if you do some crawling of Google Images and so on. This is why this is really still quite hard. Then we have high computational environmental cost. We know the models become larger. Transformer models are very, very large. Here you see one study showing that training a transformer with neural architecture searches has much higher carbon footprint than a car during one lifetime in the United States. I have to admit, maybe that's not 100% fair study, because you would not train a large transformer with neural architecture search normally. So this is a very expensive optimization technique, but still it gives you kind of a glimpse into current problems. And of course, here we talk about training, but if the model has to run in real time on the car, you know, all car components are competing for resources. You also cannot have big GPUs there on the car. And last but not least, even if we have collected training data, the environment can change. We can have different categories of objects, of activities, but also the appearance might change. This is the main topic we will talk about today. But first, briefly, related work on video-based driver activity recognition. So up to 2020 approximately, if you compare driver observation versus general computer vision activity recognition, you will see that the transition to deep learning in general activity recognition happened around 2013, where these two-stream CNNs were introduced and climbed on top of all the benchmarks. This was much slower if we look inside the vehicle. So up to 2020, most of approaches were still based on handcrafted feature descriptors, mostly derived from body pose. So it took very long time for CNNs to take over here. And what was the reason? Well, as you might think, CNNs are very, very data hungry. And here, if you look at the bottom, the evolution of data sets in general human activity recognition, where we have, okay, we start with small data sets, but already 2011, we had larger and larger data sets, and last data sets have a lot of images, 75 million images. This was not the case for driver observation datasets. They were generally much smaller, but they were also mostly not public with some exceptions. Another thing is that they only considered manual driving. So basically you could not do that much, maybe driving, non-driving, being on the phone and so on. But with the increasing automation, people can do more and more inside the vehicle. And this is why, well, what can you do if you don't have enough training data? The first thing you can do is just collect training data, and this is what we did back then. So 2019, we collected the driver neck data set, which is, as far as I know, still the largest available public data sets for driver activity recognition. This is meant for recognizing what the human is doing inside an highly automated vehicle. So we have 83 action classes, and of course many actions are allowed there, which you usually would not be allowed to do when you're behind the steering wheel if you have to drive the car. So we kind of try to already predict what the driver is going to be doing when you are allowed to do a lot behind the steering wheel. So of course, we could not do this. Just while driving on highways, because we had highly destructive activities. This is why, yes, this was collected in a simulator, but it was in a real car. So basically, we had a real Audi here, and around we had these screens where the driving was projected, and in fact, you had kind of feedback. So when you were steering the steering wheel, you had the visual feedback on these screens. So using this data set, so we equipped this Audi with many cameras. I think altogether there were 6 different cameras. And this is still the largest available data set for driver activity recognition, 83 classes. It's hierarchical annotation. And it's a multimodal data set. We have color depth and near infrared videos. So here a glimpse into the modalities. We also provide the 3D body poses and environment model. And here you can see the annotation distribution for different activities. And the main takeaway here, yes, it is unbalanced because we tried to keep some level of realism. So the person was told what to do, what task to solve behind the steering wheel, but we did not tell exactly what to do. So there was some exactly how to accomplish this task. So there was some freedom, and this kind of resulted in this very unbalanced distribution of classes, but this is quite common for real data sets. So here you can just see a small demo of a neural network doing recognition in our data set. So so this shows the automated mode, but we also had manual driving. That's just what I want to say. So another thing you can do if you cannot collect training data is you can use simulations. You all know there are already many simulations for robotics, and driving tasks. However, as it comes to perception of humans, there is much, much less. There is a lot of, as it comes to body pose or body shape, but as it comes to high level understanding of activities, there is much less. And here I just want to make some advertisements to our other data sets for synthetic to real activity recognition. One of them, the synth dataset, is in fact presented here at ICRA. So check our paper and use our datasets if you're interested in this. But now I'm coming more to a bit more methodological part of our talk. So what can you do if you don't have enough training data besides those just annotating and collecting data and using simulations? Of course, there are many techniques where you can use small amount of data plus pre-training, data augmentation, few short learning, or you can have semi-weekly self-supervision to kind of get cheaper, noisy, or use cheaper, noisy and partial labels, and you can use zero-shot learning, especially with today's foundation models. But let us just assume that we have collected enough training data and this is not a problem. What happens if the circumstances change? And here we distinguish between two things. First, domain shift. So we talk about two concepts: label spaces, what task do we want to solve, which categories do we want to recognize, and feature spaces, which is basically how what is the appearance of our data. And first, what is if the feature spaces change? This could be, for example, if we transition from synthetic to real data, or if the camera angle changes, but there are many different domain shifts, different lighting conditions, human appearances. So this is when we talk about the task of domain generalization or domain adaptation, or if we have different label spaces, we commonly talk about the so-called concept drift. And this is where we come into the topic of open set recognition and novelty detection. And this is something I want to talk about now. So until also around 2020, for driver activity recognition, we assumed that all classes were known a priori, and this is of course not realistic because we can always encounter novelty. And this is why we need models which can distinguish between known and unknown. And back then we created the open set versions of the drive and act data set. We also did similar things for general human activity recognition data sets, where we basically split our classes into known and unknown. And the task was to recognize the known classes while additionally being able to reject the unknown class. We are, of course, not the first one addressing the open set recognition task for still images. This was already done quite a lot, and here you can see a glimpse of related work, kind of different types of approaches. One class SVM was very common for a long time. Ensembles, where you do many forward passes and then see how models disagree, is very common, or reconstruction-based approaches, where you, for example, train an autoencoder and try to and use the reconstruction error as your novelty score. So if the error is high, then you assume that you reject the sample, that it's a new class. So now I will go through a few approaches which we developed, and the first ones are kind of a bit straightforward, based on the top one softmax confidence of the model. So probably, you know, if we talk about classifier, which for example has to classify, is the driver placing an object or reading something, or is he or she driving? We would have our neural network with the last layer having the number of neurons corresponding to the number of classes. We refer to this layer as the logits layer, and it would be usually normalized with the softmax function. A normalized exponential function, so that the output sums up to 1 and kind of appears to be as probabilities. And then we use it as input to cross entropy loss and get very good recognition results. The problem is in this word appear, so it appears to be probabilities, and in fact is often used to quantify uncertainty, and also often used for open set recognition to reject kind of new classes. But there was this worrying evidence published by Guo et al. in 2016 showing that neural networks are horribly miscalibrated, meaning that if you don't do anything, that this you will often have incorrect predictions with very high top one confidence. So here, for example, 93%, but it's incorrect, or 97% also for incorrect predictions. And this is why we considered measuring also the calibration of neural networks in the task of driver activity recognition. So for still images, this has been done before, but we first just evaluated how does it work with videos, in general activity recognition and inside the vehicle. And this can be, well, formally, if we look at the space of all probabilities between 0 and 1, in our ideal model, for each possible value, our accuracy, which is kind of the probability of correct prediction, should exactly match the probability value we're currently looking at. Unfortunately, we cannot perfectly evaluate it because the space is continuous. So we discretize it using a matrix called expected calibration. Arrow here, which is nothing special, we just divide the space of probabilities into bins, and then we measure accuracy, and then for each bin we compute the distance between the model accuracy and the average confidence of samples who fell into this bin, let's say on a validation set. And then we calculate the average over all these segments, and this shows you how the model is miscalibrated. It can also be very nicely visualized as such a reliability diagram. So it shows you this partitioning of probability space, and underconfident models would be above the diagonal, and here, and overconfident would be below. And usually the model is overconfident, meaning that very often it produces very high softmax values. And first, yes, unsurprisingly, our experiments showed that yes, models are poorly calibrated. And the first thing we did is we used a very famous technique, temperature scaling, where basically you learn one single parameter tau, through which you normalize your logits, and you optimize this tau on an external calibration set. And by doing this, you get better, you get much better calibration scores. So this is the first thing that we did, and it gave us better results, but we wanted to improve it further. And here our idea was to not learn a single parameter tau, but instead to learn to infer T of Z depending on the input representation Z. Because in this case, in classical temperature scaling, you just learn tau, which is a single parameter for all samples. Instead, what we do is, instead of tau, we learn tau of Z. So we additionally have an input Z, it's just representation of your input, and we infer input-dependent parameter T. And how do we learn it? Well, we learn it with a neural network. So we simply have this additional neural network called calibrated action recognition with input guidance. And what it does is we have this dynamic tau of Z. Here we see that during training, in fact, this tau of Z has a certain standard deviation. So first it rises, but also it varies, which is important to say because it could also be that it converges to a single value, which would basically mean the normal temperature scaling. And what we get here is what we see in our results is that, in fact, in terms of calibration, temperature scaling already lowers expected calibration error by a lot, but through the carrying model, we improve it even further. However, I have to say that there is one weak spot of such models, namely they are optimized on this special held out validation set. So these are post hoc calibration methods. And you can see very nicely here that they did not work for classes which are underrepresented, because we did not have much data to calibrate the model well for them. And this is why the weak spot is of such post hoc calibration method is generally distributional shifts and novelty, because we conduct this post-hoc calibration on this extra validation set, but we don't have it. But if we want to use it, in fact, to detect novelty, then we it directly contradicts the notion that our training data follows the distribution of this held out set. And this is what we see here. So using the Kering model for novelty detection, so in the open set case, in fact, improves the results very slightly, but this improvement is very, very, very small. And this is how I come to the next model which we developed to detect drive activities not seen before, namely these are methods based on the epistemic uncertainty of the classifier. Maybe you already know this categorization. There are many different categorizations of uncertainty, but the most common one is into epistemic or model uncertainty, or aleatoric or data uncertainty, for example, noise. And epistemic uncertainty is explicitly explicitly developed to measure, defined to be linked to what your model doesn't know. So in theory, it can be 0 if we have unlimited training data. One very good framework to model epistemic uncertainty are Bayesian neural networks introduced by McKay, which basically place distributions on all weights. So the outputs also become distributions. The problem with Bayesian neural networks is that the inference is very computationally expensive. So the predictive probability would be obtained by integrating over this whole parameter space. And this is computationally intractable. The good news is that, you know, the Gall et al. In 2016 provided a theoretical proof that iteratively applying dropout at test time and computing the output statistics is a variational approximation of a Bayesian neural network. So we can approximate this in a very, very simple manner, and this is what we did. So basically, the I3D model was back then the state-of-the-art model for activity recognition and drive activity recognition, and we made the probabilistic version of it. So at inference, we kept the dropout on, and then we did stochastic forward passes. So then, and then we measured the mean and variance of the output, and our logits here, I hope you can see this, become distributions. So we can measure this uncertainty by looking at the variance of the distribution. Now, I do not have much time to go into exact detail, but this was not everything that we did. We had an additional mechanism where we did not just look at uncertainty of the top 1 neuron. This also already improved the results, but we had a voting mechanism where the individual neurons voted based on their epistemic uncertainty. You are very free to look at the paper, so we can discuss more details later. So I'm a bit over time, so that's why I will skip the details. And just to summarize here, we got very good recognition results, both for when dealing when just recognizing known and unknown classes, so formulating the task as binary classification, or open set multi-class recognition, where we have our known categories plus plus unknown. I also want to recently, so I have maybe 5 more minutes, just a very brief glimpse on our recent work, our current AAA paper, also addressing open set recognition, but now from body poses. And actually body poses are quite popular in automotive community, because you kind of get a more control over what is the input of your model. So first we identify, so the input are this kind of body pose sequences. And just to summarize, it's very brief. Our model can be seen as a multi-model ensemble, where we represent our body poses as joints, bones, and velocities. So this is not developed by us. This was been done already this kind of representation. And then we pass it to different embedding to different backbones, in this case different graph neural networks. Here you see their names, so these are kind of already established benchmarks in this field. And then for training we use, so on our known classes we use first the cross entropy loss. This is nothing special, so this is what you usually do. Additionally, what we do is we use the cross mean maximal discrepancy across MMD. So this is MMD is a way for measure differences between different distributions, and here we measure it in a special way where we differentiate between intramodality differences and intermodality differences, and then we compute, we see how much they differ, and we try to integrate it in our loss in a way that we kind of minimize the distances between different embeddings of different modalities here. And the cool thing is that in fact it improves our our open set recognition when we have this additional minimization objective by a lot. And just to summarize the other tasks, we also have a distance-based approach where we additionally measure distances of a new sample to embeddings, to the multimodal embeddings of the training data, and use these distances to normalize our logits. And just to summarize it, the main takeaways is both using this cross MMD minimization additionally, and this distance-based ensemble improve the open set recognition results from body poses significantly. And in general, not surprisingly, but if you use this ensemble-based method, so velocities, bones, and joints together versus using them individually, we get much better results. So I am massively over time. This is why I will skip a bit. So I also wanted to talk about what happens if we have different feature spaces, and talk about our domain shift, domain adaptation work. But I will skip it a little bit, and just I will briefly touch on two topics before we conclude. So first, what we talked about now is how can we detect new unknown activities, driver activities. But what about resource efficiency? Because I think this is also one big problem of modern neural networks, and there are different techniques to address this. In this particular work, we combine two famous approaches for driver activity recognition. So this was published in IROS 2023. You can also get the code. So here we combine quantization. Quantization is a famous technique to get low bit weights and reduce computational complexity of your model with student-teacher distillation. So we apply quantization, and then we additionally try to distill knowledge from our large teacher model to our small and quantized model. And by doing this, here we can see some results. So here is our teacher model. We see the CPU time for inference and the accuracy. And we see that if our small model is MobileNet, if we just use it, we are here. And then through quantization, we make it even smaller. And applying then our quantized distillation technique gives us even better accuracy, efficiency trade-off. So I highly recommend you checking the paper. And the very final thing I want to say, so we focused on driver activity recognition, but what about prediction? And I have to say that when we talk about driver observation, if we talk about high-level predictions, so predicting what the driver is going to do next semantically, not about the motion, but semantically, I want to highlight this Brain for Cars datasets. This is the state-of-the-art dataset for recognizing what the driver is going to do next. Yet, The approaches are very similar because in the end you have a video, a sequence of frames, and the task is to predict what will happen in the future. So input and output structure are very, very similar. And here we also have one work where we use optical flow on the brain for cars data set, combined with a 3D CNN and an LSTM, and we got quite good results. But this was 2019, so there was also other work since then. But I would argue that most of the approaches we introduced now today would also be transferable to this task. And if you're interested in prediction, check out this Brain for Cars dataset. So thank you for your attention. I'm sorry that I am a bit over time. I know you have now the coffee break, and I'm very happy to take any questions. Thank you.
Right. Thank you for the very insightful presentation. Anyone has a question? The microphones are working.
Hello, can you hear me online?
Not very loud, but I can try.
Okay. So one quick question. Probably you mentioned about it. What are the inputs actually to the network you're using? RGB, or you have to try with thermal images or something?
Yeah, so basically it's a video. So usually it's a sequence of around 32 frames, and yes, it's RGB. Interestingly, even if we use let's say near infrared data, we usually encode it as RGB because the models are always pre-trained on the RGB data sets. So
you have the same results on also infrared images, or these were mostly on the RGB data?
So the data sets we work on are usually multi-model and have both. But so we have both near infrared images and RGB data and also depth data, but usually we'll code everything as videos, and the input would be, since we use pre-trained models, the input would be basically very similar as the one to these backbones. So it would be still kind of a video with 3 channels. Yeah, there are some exceptions. So in the last work I showed, where we use optical flow, it was in fact the displacement vector of each pixel. So it depends, of course, a bit on the modality you use, but usually it's a video snippet of around 32 frames, sometimes 16, sometimes 64, and yeah.
Thank you. Thank you so much. Do we have any further questions? I just have a very small one, a curiosity. In the very beginning, you've shown a decomposition into dangerous and non-dangerous actions. There was this 2-dimensional graph. Can you show it again, just very briefly? I thought it was curious. I wanted to see what was the other axis.
So you can see it now, right?
Low risk, high risk. Ah, it was the frequency.
So actually, this is the study. I think it's cited here, here below. So this is, yeah, I think this is this study. The last citation here, where basically they try to quantify different secondary activities in terms of how often people are engaged in it versus the risk. And you can see you have rare low risk activities like makeup, and low risk high common activities like, for example, adjusting climate control and so on. And then you have, for example, high risk frequent activities like passengers being disruptive. So this is ranked as very, very high. However, I have to mention regarding this particular study, so they have this very cool visualization, but this is, they interviewed a lot of people. So this is based on self-assessment, which means that, for example, if you have here makeup is low risk, this is what people kind of said it is low risk. It does not mean that, in fact, it has less accidents if people, you know, apply makeup or shave inside the car. But there are also some other studies which, like this 100 car study, which in fact calculate accident odds for different activities.
Okay, I see. Thank you so much. Then let's thank the speaker again.
Thank you.